Okay, inverse operations. Find the inverse of the following functions algebraically and then evaluate the function. So here's what we have for example A. We have f of x or y equals 2x plus 5. In order to find an inverse operation, it's pretty simple. What you want to do is you just simply want to swap the y and the x. So I'm going to say it again. This function is y equals 2x plus 5. If we're going to find the inverse, I'm going to change it to x equals 2y plus 5. And now we're going to solve for y. I'm going to write this down because it might help you in case you have some difficulty with these. Yeah. Okay. Whenever we're solving for a variable in an equation, most of the time you're going to do your order of operations backwards. You're looking to see if we're solving for y, is there anything we can add or subtract away from y first? There is. We can subtract 5 from both sides. Okay, we have taken care of addition and subtraction. So now do we have anything that we need to multiply or divide away from y? Yeah, we do. We would need to divide both sides by 2. Leaving us with x minus 5, all divided by 2 is equal to y. Now this symbol right here that I'm just about to put above the y, hopefully that's not going to cause too much confusion. I don't want you to worry too much about it, but that just simply means this is an inverse of another operation. That's all that means. So that would be your answer for the first part here. This f prime of x there, x minus 5 over 2. That is our answer. That is the inverse. That's it. Simply switch x and y and then solve for y. Now we're finding f of 1. That's what they want us to do next. So we're going to locate the f function, which is here. Everywhere you see an x, plug in a 1 and then do your math. 2 times 1 is 2 and 2 add 5 is 7. So f of 1, 7. Now here, notice you see that little mark above the f there, that little prime. I've heard of it referred to as prime, f prime of 7. What that means is now you want to take 7 and substitute it in the inverse operation. So make sure you're looking at what symbols are they using. Are they using any symbols here? So we're now going to take 7 and substitute it here. So 7 minus 5 over 2, which would reduce to 2 over 2, and that would give us 1. What do you think so far? That is exactly what it means. All right, example B. We first need to find the inverse. So as I mentioned, instead of g of x equals, this is y equals negative 1 over 2 x squared minus 4. Let's swap the y and the x variable. Now this is where that little roadmap I gave you might help. Okay, because we have several different operations that we have to work with here in order to isolate y. First, is there anything we can add or subtract? Yes. All right, somebody say it. Good. Yeah, the negative 4. So let's add that to both sides. Squared. Okay, we've taken care of addition and subtraction. Now, do we have anything that we can multiply or divide away? And we do. That negative 1/2, we want to multiply by the reciprocal of that. So we're going to multiply both sides of the equation by negative 2. I'm going to go ahead and distribute that negative 2 throughout the parentheses here. Okay, we've taken care of multiplication / division. Now, do we have an exponent that we need to get rid of? Yes. And the way that you eliminate a square is you take the square root. Now, be careful here. Our answer is y equals plus or minus square root of negative 2x minus 8. If you're solving for x squared, y squared, whatever squared, and you take the square root, Your answer is plus or minus that result. So we have now found the inverse. I'm going to write that down here. Y equals plus or minus 2x minus 8. Okay, so if we're going to find g of -4, notice that g does not have that little prime signal above it. So we want to substitute -4 into the original function. Everywhere we see an x. But of course not the g of x, because that's really y. We're substituting -4 squared minus 4. Okay, I'm going to challenge you. Solve this on your own. I'm going to be silent and solve it myself. Let's see if you remember how to solve these types of things. -12. Good job. Okay, now we have g prime of -12, or the inverse. So let's take -12, substitute it into our inverse function, and let's see what we get. Same thing here. Try to work this one on your own. Didn't it? Remember, you need the plus or minus symbol. Okay, if you just had 4, well, you're half right, but it's also -4. So plus or minus 4 there. What do you think so far? Hopefully nothing too hard. This next test should be pretty easy if it was all this. All right, next, a function whose inverse is also a function is called a one-to-one function. We actually went over that like a unit, not last unit, but maybe the one before that or before that. And then we didn't see it like ever. Well, here it is again. The way that you can test if they have given you a graph, whether or not a function is one-to-one, is you can do the horizontal line test. As long as it passes the horizontal line test, meaning it doesn't cross the graph more than once, then it is a one-to-one function. So this one would be a one-to-one. This one would not, because it would be crossing the graph there and there. So since it crosses twice, not a one-to-one function. That's how you can tell visually if it gives you a graph. Algebraically, however, we would have to do something a little bit different. So look at the bottom here. They have provided us two functions. F of x equals 3x minus 5, and then g of x equals x plus 5 over 3. And they're asking, are these inverse operations of one another? Well, I guess you could do what we just did, swap x and y, but there's another way you can do it too. And this is the way that they want you to do it. But truthfully, I don't really prefer either. I mean, whatever way you'd want to do it. So here's what you want to do. You want to substitute one function into the other. And it doesn't really matter which one you substitute into which. I would try and be strategic about it, however, and try to do the one that would be the easiest to solve. So if I'm looking at these problems, I'm thinking it's going to be easier to take f of x and plug it into g of x. And here's what you do. So g of x is x plus 5 over 3, right? X plus 5 over 3. I'm going to do parenthesis plus 5 over 3. So instead of x plus 5 over 3, I simply did parenthesis plus 5 over 3. And now in those parentheses, I'm substituting the f of x function, which was 3x minus 5. Substitute one and the other. Reminder, doesn't matter which one you go with. This one just is probably going to be the easier one to solve. Do I need these parentheses anymore? No, no, I don't. So I'm going to get rid of them. Now begin by simplifying anything on the numerator first. You can probably tell, well, the 5s are going to cancel one another out. That would leave us with 3x over 3. The 3's cancel one another out, leaving you with x. What that means is These are inverse operations. Anytime you plug in one function to the other and you're left with x and only x, they are inverse operations. So yes, and we proved it, by the way, by doing the math algebraically. What if it was negative x? Would they be inverse operations? No, they would not. Okay, we already did that. You're going to want to, if you haven't, just remind me after notes. You're going to want this column filled in, that column filled in, and then graph. But I think that hopefully I gave you guys enough time. All right, now on this page, page 3, fill in these values here. We have 1/2, we have 1, and we have 2. 1/2, 1, and 2. Now what we're going to do is we're going to be graphing exponential functions. And we're going to begin right here where it asks us, what is the equation for the asymptote of the parent function? So we just got finished with unit 10 where we were dealing with asymptotes all over the place. Well, an exponential function also has an asymptote, and it is a horizontal asymptote. And if we're dealing with the parent function, which we are, it's going to be y equals 0. That is the horizontal asymptote. Now, sometimes it's easy to get confused on, well, if it's an exponential function, is it a horizontal asymptote or is it vertical? So here's a little cheat that you can use if you have difficulty remember. If I write the word, I'm just going to abbreviate exp, I'm abbreviating exponent, and then draw arrows on the e's, those are horizontal arrows, right? So an exponential function is going to have a horizontal asymptote. Okay, now let's look at example 1. If we had to graph one of these things, we have to graph 2 raised to the x minus 3 power. Now, that x and the minus 3, that, if you don't remember, that is a horizontal shift. Is it left 3 or right 3? It's right 3. Very good. Anything that is impacting x is actually opposite of what you think it would be. So whenever we're going to graph these, we're going to use a transformation table. The only transformation to this graph is we are going right 3. So right here, I'm going to write x plus 3. There is no change that is occurring to y. So right here, we're just going to write y. Now, here's what you're going to do. Let me cover up these values real quick. Oh, well, okay. We're simply going to we're going to start with the x values, and we're going to plug them in here for x into the transformation table. So take -1, substitute it here for x. -1 plus 3 is 2. Take 0, substitute it for x. 0 plus 3 is 3. Take 1, substitute it. 1 plus 3 is 4. Here, we're now going to take the y values and substitute them for y, but since there's no change, it's going to be exactly the same. 1/2 is still 1/2. 1 is still 1, and 2 is still 2. Yes?
So why would you go up there? Why would you back between?
You want to use the values from the parent table. This is the parent function, by the way. We already wrote that down here, but we didn't include every single one. We only needed a few, right? So whenever you're using a transformation table, you want to use the parent table in order to build your transformation table. So anytime you're doing an exponential function that is base 2, you're going to want to use these numbers always and then plug them in your transformation. That's a good question. Thank you. I assumed we all knew that, and that was a bad assumption on my part because, well, I've been doing this for a long time, and I'm the only one who has been doing this for a long time. So good question. All right. So now we're going to plot. So 2, 1/2. Go right 2 and up about 1/2. 3, 1, go right 3 up 1. And then 4, 2, right 4 up 2. Now here's what I'm going to do. I haven't done this yet. I'm going to plot the horizontal asymptote. Remember, there's no change in y, right? Since this is a horizontal asymptote. Good thing you are kindergartners. That would have gone over well. An asymptote, any change in y is going to change the asymptote, but there is no change in y. So it's still y equals 0. And exponential functions, more times than not, are going to start here at the left, and they're going to be really, 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 really close to the asymptote. And then as they approach those coordinates, they're going to shoot up. And that's good enough. All righty. Now for example 2, do we have any impact on x, on our x value there? None. So here in this transformation table, just write x. Now that -4, by the way, the only thing that will impact x is if it's up there with the exponent, okay? Everything else is going to impact y. So here we have a vertical shift down 4. So in our transformation table, we would write y -4. That's also going to now change our asymptote. So our horizontal asymptote is now going through the y-axis at -4, -1, -2, -3, -4. Now, in order to build the transformation table, we're going to use the parent table, and we're going to plug it in here. So our x values of the parent table, we're going to plug in here, but there's no change to them because there was no change in x. -1 is still -1, 0 is still 0, and 1 is still 1. Okay, now if we take the y values from the parent table and transfer them here to the transformation table, 1/2 -4, that is -3/2, -3.5. 1 - 4, that's -3. 2 - 4, that's -2. Now do your best to plot these points and graph -1/2. More times than not. I think it is safe to assume in this class it's going to be. All right, we're not going to necessarily graph 3 and 4, but I do want to show you what the transformation tables would look like. So for this one here, once again, there is no impact on x, so it would just be x. That 2 there, I also hesitated to mention this. That's just the base. That 2 right there, that's not a stretch. That's not a shrink, nothing like that. So don't think we have to multiply y by 2, okay?
Will that ever change?
It could change, and I'm going to show you what it would look like in just a second, okay? Let me get through this one. That's a very good question. So here, that negative in front of 2, just put a negative y. So all your y values, if they're negative, they're now going to be positive when you plug them in. If they're positive, they're going to be negative. All right, for this one here, pretty much similar. We do have an impact on x, so we would just put -x. That negative in front of the 2 would be -y. Substitute parent into that into this transformation table, and then plot those points, and you'll be good to go. So if you happen to have a stretch, this is what it's going to look like. It could look something like this. 3 times. You see that? That's what a stretch would look like in an exponential function. Okay, let's go ahead and move over to the backside and now graph logarithmic functions. Now on page 2 of our notes, we wrote down several different numbers for our logarithmic functions. We don't want to use those. We just want to use these 3 right here. So we're going to use 1/2, we're going to use 1, and we're going to use 2. What is the equation for the asymptote of the parent function? This one is going to be x equals 0. X equals 0, that's going to produce a vertical asymptote. And in case you need a little reminder, if you write the word log, which is short, which is short for logarithm, you could draw arrows on the L. I sure could use a 4-day weekend. What about y'all? Okay. All right, let's get to it. All right, looking here. Example 1, we have log base 2 of x plus 3. That's transformation left or right, opposite of what you think it would be. We're actually shifting left 3. So in our transformation table, x minus 3. There is no change in y, so just put y. We have just built our transformation table. We're now going to take the parent values, substitute them here for x. So 1/2 minus 3, that's negative 2.5. 1 minus 3 is negative 2. 2 minus 3 is negative 1. Now, anytime there is a change in x, that is going to change your vertical asymptote. So this graph is shifting left 3, right? We've already notated that here. So that means our vertical asymptote is going to go -1, -2, -3 spaces. And now here's our vertical asymptote. Oh my, I forgot to plug in the y values. Look at that. So if we take -1, plug it in here for y, none of these are going to change. Your y values are going to be the same. And now we plot beginning with -2.5, -1. -2, 0, -1. And most of your logarithmic functions are going to start from the bottom, very close to the vertical asymptote, and then begin to curve once they reach those coordinates. Please look at example 2. This is a very common error. With example 2, that is not a change in x, that is a change in y. The way that you can tell in a logarithmic function, if there's a change in x, is it's going to be in parentheses with the x. Okay, has to be in parentheses. So here there is no impact on x, but we are shifting down 5. So that would be y minus 5 here in our transformation table. Since there is no change in x, that means our vertical asymptote is still going to be at x equals 0. I would like for you to now build your transformation table in Graph. Why does it seem that all the ones I have you guys graph, like it doesn't even fit? If you got this, you're on the right track, okay?
You start on the bottom.
We're going to start on the bottom, which is why I extended the vertical asymptote, because this one would start way down here and then begin to curve as it approaches those coordinates. All right, we are not going to graph 3 and 4, but at least try and put the transformations here and there. I'm not interested with the coordinates, the values, but just could you tell me what the transformations are for 3 and 4? And then do you think you'd be able to take the parent table and substitute them here and then come up? That's it. That's all it is.